When we gaze at the night sky, we're looking back billions of years into the universe's history. The light from distant galaxies has crossed unimaginable distances to reach us. On the largest scales, the universe appears almost perfectly flat, a cosmic canvas stretched across 13.8 billion years. This is surprising given that everything else in the cosmos, planets, stars, galaxies, is curved or warped. Yet, zooming out, all that curvature vanishes. The universe follows the simple rules of geometry we learn in school. Why is this flatness so mysterious? Because the universe is filled with matter and energy, all of which should warp space. With so much mass, we'd expect the universe to be noticeably curved. Instead, it's balanced on a razor's edge. The universe expands, but in a way that preserves this flatness, as if it's coasting along a perfectly straight path. This cosmic flatness is one of the great puzzles of modern cosmology. If the conditions after the Big Bang had been even slightly different, the universe could have collapsed or expanded too quickly for stars and galaxies to form. The fact that we're here means we live in a universe that's been fine-tuned from the very beginning. This flatness is a clue, a whisper from the dawn of time. It's a mystery that takes us right back to the origin of everything. To understand why a flat universe is so strange, we need to grasp what it means for space to be curved. General relativity tells us that space and time form a flexible fabric, spacetime, warped by matter and energy. Imagine a stretched rubber sheet. Place a heavy ball in the center, and it creates a dip. That's how mass bends spacetime. Gravity isn't a force pulling objects together, it's objects following the curves in spacetime. Every planet, star, and galaxy creates its own dimple in this cosmic fabric. The more mass, the deeper the curve. The overall shape of the universe depends on the sum of all these curves. If you could add up all the matter and energy, you'd determine the universe's geometry. Is it curved like a ball, warped like a saddle, or flat like a sheet? The answer depends on the total density of everything in existence. This is the central question cosmologists ask when measuring the shape of space. The universe's geometry isn't just a mathematical curiosity, it determines its fate. And as we'll see, our universe's shape is extraordinary. The universe can have three possible shapes: closed, open, or flat. A closed universe has so much matter that space curves back on itself, like the surface of a sphere. Travel far enough, and you'd return to your starting point. In an open universe, there's too little matter, so space curves outward, like a saddle, and expands forever. Triangles in a closed universe have angles adding up to more than 180 degrees. In an open universe, less than 180. The third option is a flat universe, balanced perfectly between the two. Here, space follows the familiar rules of geometry. Parallel lines stay parallel, and triangles add up to 180 degrees. A flat universe expands forever, but at a rate that slows over time. Observations of the cosmic microwave background show our universe is astonishingly flat. This flatness is the Goldilocks case, neither collapsing nor flying apart. The geometry of our world is the geometry of a simple, flat sheet. But this perfect balance raises a profound question. How did the universe end up so precisely flat? The discovery of a flat universe is one of science's most profound puzzles. The universe's geometry is set by its total density of matter and energy. If the density is above a critical value, the universe is closed. Below it, open. Exactly at it, flat. Our universe's density is incredibly close to this critical value, a balance so delicate that any tiny deviation after the Big Bang would have been magnified over billions of years. If the early universe had been even slightly denser, it would have collapsed in a big crunch. If it had been less dense, it would have expanded too quickly for galaxies or stars to form. For the universe to be as flat as we see today, its density 1 second after the Big Bang had to be tuned to 1 part in a quadrillion. It's like balancing a pencil on its tip for 13.8 billion years. This is the heart of the flatness problem. The universe didn't just start close to flat, it started almost perfectly flat. How could such precision arise naturally? The flatness problem puzzled cosmologists for decades, until the theory of cosmic inflation emerged. Inflation proposes that, in the first fraction of a second after the Big Bang, the universe underwent a burst of rapid, exponential expansion. During this brief moment, the universe grew from subatomic size to something the size of a grapefruit. This violent stretching flattened any initial curvature, just as inflating a wrinkled balloon smooths its surface. Inflation made the observable universe appear flat, even if it started out curved. The process didn't require special initial conditions. It naturally drove the universe toward flatness. After inflation ended, the universe was left smooth, flat, and ready for the Big Bang's hot, dense expansion. Inflation turns an improbable coincidence into an expected outcome. The universe is flat not by chance, but because of this extraordinary process. Inflation elegantly solves the flatness problem, but it also opens up new mysteries. If inflation flattened the universe, what powered this explosive expansion? The leading idea is a new energy field, the Inflaton, never directly observed. The Inflaton field filled all of space, with a strange property negative pressure, acting like anti-gravity. For a brief instant, this field dominated the cosmos, driving exponential expansion. Then, as the Inflaton decayed, it released energy, creating the hot, dense universe we know as the Big Bang. Inflation isn't an alternative to the Big Bang. It's the prequel, setting the stage for everything that followed. The Inflaton remains hypothetical. We haven't detected its particles or know its true nature. Some theories suggest our universe is just one bubble in a vast, eternally inflating multiverse. While speculative, these ideas show how the quest to understand flatness leads us to the edge of reality itself. The search for the Inflaton is a search for the ultimate origins of everything. The universe's flatness is more than a geometric curiosity, it's a clue to our cosmic origins. This delicate balance made galaxies, stars, and life possible. The flatness we observe is a reflection of our own existence, whether explained by inflation or something yet unknown. It forces us to confront the deepest questions about the cosmos. Why did the universe begin this way? Was inflation a one-time event or part of a larger process? As we build better telescopes and experiments, we search for evidence, like primordial gravitational waves, that could confirm inflation. The quest is to turn theory into fact, to find the fossil echoes of the universe's birth. The flatness of space connects us to the cosmos, balanced on a knife's edge since the dawn of time. The simple geometry of triangles across billions of light-years is a message from the beginning. The flat, endless sky is full of answers, waiting to be found.